free as a bird on BBC Learning Zone now as the Open University discovers the mathematics behind unpowered flight.
For thousands of years, men have watched the birds in flight and dreamed of the time when they too could leave the Earth and fly through space. But it was not until the first half of the 19th century that the pioneers of flying began to experiment scientifically with gliders. That is, airplanes not provided with an engine. The early efforts of these bold experimenters prepared the way for the modern aeroplane. But gliding is a fascinating form of sport, and today, all over the world, men and women are learning the ways and moods of the air at flying clubs.
From the earliest days of gliding to now, there's been a constant process of changing and modifying designs. That process has involved making and refining mathematical models to make a glider that performs as well as possible. Having no engine, a glider needs a hand to get airborne. After that, it's at the mercy of gravity and air currents. But that's not as restricting as you might think. There are many factors which will affect the ability of a glider to fly from one place to another. Not least, there's the weather, and in particular the speed and direction of the wind. There's the glider's mass and also the angle of glide to be taken into account. And as if this wasn't enough, the pilot has constantly to seek out sources of lift to compensate for the glider's otherwise continuous descent through the air. Mathematical modelling has a major role here, particularly in modern racing competitions. One such competition involves mainly British pilots in an event organised at Le Blanc in France. It's known as the British Overseas Nationals, and the skies of central France are favoured for their more reliable weather. These pilots are going to fly a modest task by modern competition standards.
Back in this direction.
From Le Blanc, they'll have to complete a four-pointed course, which will take them at least 240 kilometres before they return to the starting point. But of course, a closed circuit like this means that some stretches of the journey are going to involve flying into any prevailing wind, and that presents problems for pilots of engineless aircraft.
To the right. I think most of you would have found the turn points. We have rolling a start for both tasks, and the first turning point on the A task is Port de Peel, up the river to the northwest. Second turning point, Valençay, and then Shervig Newcastle, and return. Finish line will be 05. So we'll see you guys on the grid at 12:15 for launching at 12:30.
You'll be seeing that an important aim of glider design over the past 40 or 50 years has been the improvement of the into-wind performance. Also, what's quite surprising is that far from it being desirable to achieve the very lightest design, gliders can actually benefit from extra weight. This isn't fuel being poured into the wings, it's water ballast. It's the cheapest way of getting extra weight on board, which can then be dumped during the flight if necessary. In today's competition, a glider pilot flies a very sophisticated machine with all the latest flying instruments, including some of the most modern satellite navigation systems. Even so, some basic instruments have been common in gliders for many years.
This is a fairly standard training glider. I'll go through the main instruments used in flight. First is the altimeter, which measures the height of the aircraft in feet, normally above the ground point where you started. Then we have the airspeed indicator, which gives the speed along the direction of travel, and the variometer, an extremely sensitive instrument which gives the vertical speed of the glider to and from the ground. You can see how sensitive it is from the fact that it's moving around slightly, just with a few gusts of air on the ground. Both of these are calibrated in knots. That's a nautical mile per hour. And 1 nautical mile per hour is roughly the same as half a metre per second.
The gliders in this French competition could well be flying for 3 hours or more today. Yet at the end of the race, pilots might be separated by only a matter of seconds. Of great significance is the gliding performance that each glider has been designed for. Just what gliding performance means and how it affects this race, we'll be exploring later on. But first, let's return to the 1930s for a lesson in flying.
At Dunstable, the London Gliding Club with 300 members and 25 machines have their headquarters. Let us visit the club to see how gliding is learned. The beginner learns the first stages of gliding on this elementary machine, which is called a ground hopper. He straps himself into his seat and is shown how to work the controls. They're exactly the same as in an aeroplane. These pedals control the movements of the rudder. Moving the stick backwards or forwards controls the elevation of the machine for climbing or for diving. Moving it right or left works the ailerons or adjustable parts of the wing and controls banking.
The London Gliding Club remains very active to this day at its original site next to the hills of Dunstable Downs. One of the early flyers at Dunstable was Anne Welch, who went on to become the manager of the British gliding team.
Having no engine, gliders needed a hill simply to get into the air. Sometimes simply by pushing and sometimes using a rubber rope called a bungee.
6 men stretching the elastic rope send the machine high into the air when it's released, giving the pilot a chance to try the different controls.
These primaries were designed intentionally to teach people to fly before they could get their sticky hands on something much better.
Are you ready? Walk and run.
They didn't have much performance. That was intentional, so there's no question of the misguided student vanishing over the horizon. You had to stop quite soon, and because if you didn't, the glider did stop for you.
He's launched for the first time from a hilltop. It's a nervous moment, but if he's successful in defying the law of gravity for a triumphal half minute, he is granted his A license.
But the early gliders had so little performance that all they could do was to land down at the bottom of the hill. If they got that far, some of them, even the very early ones, actually made it to the ground before they got to the bottom of the hill.
Whereas training gliders were purposely designed to glide badly, this glider, the Röhn-Sperber from 1937, is a sailplane designed for soaring flight. Given enough height, it could stay aloft to fly cross-country. That's 2 gliders designed for 2 very different performances. Take the primary, for instance. For every 20 meters forward, say, the primary will descend about 4 meters, giving a glide ratio or glide angle of around 5:1. Whereas the Röhn-Sperber is designed for a flatter glide, and so over the same horizontal distance it drops a quarter as far, with a glide angle down to 20:1. Why is there such a difference in performance? The Dagling primary, with an open cockpit, has very poor streamlining, and the air resistance rapidly increases with the drag. whereas the Röhnsberger loses less energy through drag, so its better aerodynamics allow it to soar. Travel through the air at about 30 knots, and the Röhnsberger will descend at about 1.5 knots. But this descent can be countered if there's a component of airflow which is rising. A strong enough upwards airflow can not only stop a glider's fall, it can even allow a glider to climb. One place where you might find rising air is where wind blows onto a ridge of hills and is deflected up.
One or two pilots found that they could stay up in this hill lift, this ridge lift, without losing height, and thus extend the length of their flight. And then one or two of the bolder ones would do a turn at the end of the ridge and fly back along the ridge. And then they would find that they were getting excellent soaring, provided the wind was blowing onto the hill. This helped the design of gliders to change, since to make the most of hill lift, they built very big span gliders which would fly very slowly, and so they could go turning in and out of all the little gullies and ridges and stay airborne.
From the top of the hill here at Dunstable, we can see the London Gliding Club laid out below us, and we can also see gliders flying above us. The ridge here is only about a couple of miles long, and there's an awful lot of countryside out there without ridges, so when people are flying cross-country there, how would they find the lift?
Well, they certainly wouldn't limit themselves to a small ridge, but you look for cumulus clouds, and cumulus clouds on a good day will be right to the horizon and beyond. The cumulus clouds really are signposts of thermals. Now, if the pilot gets in a thermal under a cumulus cloud, he'll circle up, flying as slowly as possible, so he gets a small turning circle up to the base of the cumulus. While he's doing that, he'll be looking ahead to see where is the next good cumulus to go for, and he will go for its thermal.
Why are cumulus clouds so closely associated with thermals? Well, sunshine heats up the surface of the Earth, and the Earth heats up the air close to it. But some parts of the land heat up more quickly than others. For example, a village will absorb heat more quickly than surrounding fields. This leads to a patch of warmer air above the houses, and since hot air rises, it detaches from the ground in due course as a rising bubble, a thermal. As this air rises, it cools, and any water vapour condenses as cotton wool-like cumulus clouds. Thermals are created all the time, but each one isn't continuous. As the hot air column rises, cold air descends from all around to be heated in turn over the hot spot. In fact, you can get a thermal forming over and over again. This speeded-up film shows the formation of thermals every 10 or 15 minutes, with a new cumulus cloud building up each time. If a glider turns tightly enough to stay within a thermal, it can gain height. Once at the top of the thermal, a glider can strike out across country by gliding down to another thermal in order to gain height again. Particularly with a following wind, gliders like the Röhnsberger could go a very long way, but a downwind journey meant that the glider needed to be retrieved. To avoid long road journeys, the Röhnsberger would have to make progress into a headwind to return. That means flying faster, and faster flying makes the performance much worse. We can demonstrate the performance penalty associated with speed in a special test flight. For a relatively small glide angle, you can assume that the horizontal speed is the same as the airspeed, and the airspeed is easy to measure, being one of the instrument displays.
I'm flying the glider now at about 50 knots, with a vertical speed of about 1.5 knots down. That gives us a glide angle of about 30 to 1. If I now increase the speed, we're now doing 80 knots, and the vertical speed is around 4 knots. So at 80 knots, my glide angle has got worse, and I'm only doing about 20 to 1.
You can plot the performance of that test flight in terms of the relationship between horizontal and vertical speeds. At 50 knots, the glider's vertical speed is about -1.5 knots, and at 80 knots, the vertical speed becomes -4 knots. Other airspeeds carry different speeds of descent, giving this performance graph, which is known as a polar curve. The highest point on the graph gives you the minimum sink speed for this glider. That's around 40 knots. It's the speed at which it should fly in thermals or other rising air to gain height as quickly as possible. The tangent from the origin to the curve touches the curve at the point with the lowest possible ratio of vertical to horizontal speed. The airspeed at this point is called the best glide speed, and it's generally slightly higher than the minimum sink speed. Now, the Röhrsperber performs well in a very narrow range of speeds. Fly at speeds much greater than 40 knots, and the Röhrsperber effectively drops out of the sky. The design of the early gliders enabled them to fly in a limited speed range, and it wasn't until after the war that designs changed sufficiently to make flying into headwinds more feasible. Thinner plywoods and better glues meant that much better performance could be achieved with wooden gliders.
Well, John, this is the K6, one of the classic gliders of the time, the early 1960s. It was a very, very popular glider. Why is it different and better than the Sperber?
Well, and it's a much cleaner design. It's more sleek, the wings are thinner, the surface finish is much improved, and the overall design is much more aerodynamic.
And what about the performance on this?
You normally can thermal between 40 and 45 knots in the K6, but flying between thermals you can fly quite satisfactorily up to 60 knots without the performance deteriorating too much.
That's great, so you've got some into-wind penetration with it.
Yes. In fact, I think that they have now achieved a 500-kilometre triangle
in a K6?
In a K6.
Oh, very successful.
Yes.
Modern gliders, like this discus, are made of new materials such as fiberglass and carbon composites, which have the very important property of being able to hold water ballast.
What performance can you get from the discus?
We have a performance of 1 in 40 to 41.
Glide ratio?
With glide ratio,
very
yes.
Nice.
With a speed of 40 knots to 100 knots with no degrade in the performance.
Tell me about your using water ballast in this.
We can take 137 kilos of water in our wings, and which we can dump through a little valve at the side here in 4 minutes just before we land.
You'd think that gliders would want to be as light as possible. It seems strange to want to make a glider heavier than it needs to be. Look at the polar curve for the discus. When the wings are filled with water, the total weight increases and the performance of the glider alters. This change can be represented by an expansion of the curve away from the origin to give a new polar curve. In this way, speeds such as the best glide speed are effectively increased by increasing the glider's mass. But there are drawbacks to weight, such as the forces that occur on landing, and if a thermal is weak, you might wish to fly slower to make tighter turns. So the ability to dump water and return to the original performance is also required. When modelling performance in moving air, you are effectively manipulating the position of the polar curve with respect to the axes. For example, if you are flying in rising air, the curve can be thought of as moving up. In the case where you're flying through still air, your progress through the air is much the same as your progress over the ground. In other words, your ground speed matches your air speed. But fly into wind, and your forward progress over the ground will be less than the speed through the air. And the overall change is illustrated by translating the polar curve to the left. In other words, flying into, say, a 50-knot headwind with an airspeed of 80 knots will result in a ground speed of 30 knots. Drawing the tangent to this new graph shows you that the best glide speed is now around 85 knots for this headwind. With a glide angle of 40:1, the Discus is more than capable of racing a triangular course, and there are several taking part in the race in France. However, getting 22 gliders into the air takes time. Let's hear from two of the pilots still waiting for launch.
Julie, you're flying a Discus today. How do you feel about that?
Good, the sky looks very good now, and there was some cirrus hanging around high cloud earlier, but that seems to be dissipating, and we've got nice cumulus around, generally around the task area. Turn the radio down. So it's looking good.
It's a good day to be flying this glider.
Yes, I would think so, yeah. I mean, you can only make that decision when you're actually up there, but I don't foresee any major problems flying this glider at all.
Well, good luck.
Thank you.
Also waiting is glider number 108, an Ash 25, with a performance of 58:1. But that performance suits some days better than others.
Is this a particularly good glider to be flying on today?
No, because this is a handicap competition, and on days when the tasks are at high speed, the gliders with the shorter wingspans actually have a handicap advantage on us, effectively. We score out on the days like yesterday when there are long glides at best glide angle. It's supposed to all average out in the end, but on fast days the small gliders have a definite advantage.
Once you've got them all up into the air, the race can commence. Then it's a matter of sitting back and waiting for them to return. But how can you confirm where they went?
We'll be able to verify the flight from a black box recorder, which is carried in the glider. And the black box recorder is something like this. And it's a small device which is plugged into a GPS, a global satellite positioning instrument. That records every 10 seconds the position of the glider, and the time and the altitude of the glider. We then take the information out of here into a computer, and we then show that information on the screen, and it will show us the exact track of the glider and the exact position at any one time, from which we can get the start time, the position at each of the turning points, and the finish time.
There's a constant process of modelling while flying, setting expected lift in thermal against appropriate glide speed. But while there are lots of aids to help reach that optimum speed, much depends on the pilot's skill at identifying promising thermals and estimating their strength. For instance, two gliders might choose different glide speeds to travel between thermals, one very fast and the other at best glide speed. The penalty accepted by the faster glider is to fall rapidly, but it will arrive at the next thermal very much sooner and have the advantage of a longer period of lift. So by the time the second glider arrives, even though it chose best glide speed, it can end up lower than its rival. This is Chauvigny Castle at the third turning point in the race. From there to the finish is what's called the final glide, and that's a race against the clock. Now the calculation that's necessary is the height that's needed to come straight into land, fast.
We hope they'll all get back, but a number of the pilots will have some difficulty during the flight. They'll miss a thermal, they maybe fly a little bit too aggressively, get too low, and they'll have to land in a field, and they'll what we call land out. And we anticipate that on most tasks we shall get maybe 15–20% will land out. Of course, if the weather becomes much more difficult than forecast, then they all will land out. But we try to design the task for an 80% return to the airfield.
In the event, the winner got back in well under 3 hours, and glider 108 wasn't very far behind.
It's nice.
Well, again, have you had a nice flight?
Yes, we had a lovely flight. It was had a bit of everything, from absolutely hurtling along at cloud base with the lift so great that we were actually travelling at about 110 knots at some times. And then around the second turning point, it suddenly started to look a lot different, and we found ourselves scrabbling around, taking 1.5 knot stuff just to keep in the action for a while.
We're looking here at 108 in the verification. It's quite interesting to watch the deviations off track to find the good weather. On the way to the third turning point, he flies more to the north. He's got a good thermal, and now down to take the turn point, find some height to make his glide home.
Richard, what was the final glide like?
We had about a 1 in 30 glide angle, and what we did was that we kept on the 1 in 30 until we started being obviously above it, and then we gradually work up the speed, increase the speed director setting on the computer. The last bit of the glide was at something about 100 knots, but then for the very last bit, when we had a bit spare, we actually went up to about 130 knots.
Julie, you were one of the later arrivals today. Was that problems in the flight?
Not problems, more bad decision making on the latter part of the third leg, and the last leg was quite slow.
So after all, was it a good day for a discus as a glider?
Yes, it was a very good day for a discus. It wasn't a particularly good day for this pilot.
And did you keep the ballast all the way around?
I dumped the ballast after the second turning point, which was balancé, because we were running into the cirrus and under the weaker conditions, and I just thought, get rid of it to help the glider climb. Because climbing's important. If you're not climbing in the glider, you're not going to go anywhere.
With hindsight, would you have done things differently?
It's difficult for me to say whether I would have done things differently. It's interesting for me to go and talk to other pilots who went faster and find out what they did. Also, tomorrow at briefing, the winner will describe what he did. He was very much faster than everybody else, and it'll be very useful for us all to find out what Russell did.
The time chosen to actually start the race can play a big part in the final outcome.
Probably the best decision I made was right at the beginning and starting as early as I possibly could. Some of my competitors, my main arch rivals, they started 5 minutes behind me. I had a good run round most of the task that put me, say, 15–20 minutes ahead of the pack, coming to the final stages, and that made all the difference. 10 minutes gained early on in the flight is crucial.
We've been looking at a range of gliders. Today's international competitions attract the most up-to-date and intensively designed aircraft. But even so, great enjoyment can be had in very much humbler gliders. All that's needed is for the pilot to have a model of performance and know how to apply it. In fact, over the years, it's been the demands from pilots which have led to better designs, and then in turn these improved designs have inspired the pilots to attempt more and more. And so, the design loop continues.